Welcome. We've seen in the previous clip the main morphological domains of the sea and ocean: the coastal region, the continental shelf and slope, and eventually the abyssal plain. We will look today at how water masses move in these large domains and address currents, tides, and waves. The understanding of movement of water masses is crucial for our ability to predict how sediments are eroded, transported, and deposited. This knowledge is key to answer questions such as how much sediments will we find in a specific place? Will these sediments be sand-rich or, on the opposite, predominantly shaly? At the very large scale, global currents play a key role in controlling climate, biological processes, and transporting sediments, and are responsible for many other phenomena. Currents are also active in the deep oceans, although with low speed and limited capacity to transport sediments. When currents move towards the continent, they will interact with the continental shelf and then with the coastal domain. Their movement is conditioned by seafloor topography. Water masses transported towards the coast are diverted, causing potentially very important along-shore currents, key for the erosion, transport, and sedimentation of sands. We will look in more detail at these phenomena at a later stage. A very important process controlling water movements on the shelf and around the coastal domains are tides. Tides are movements of water masses controlled by the gravitational forces exerted by the moon and the sun on the rotating Earth. In a graph displaying tides-related sea level changes, you see the well-known daily cyclicity driven by the attraction of the moon and by the centrifugal force of the Earth. The diagram shows also oscillations operated at larger time scales, for instance, the 28 days monthly cyclicity. This is associated with the relative position between Moon and Earth. Tides result in major horizontal vertical movements of water. In shallow water, a small increase in sea level corresponds to a large displacement of the coastline. Consequently, large domains are regularly, twice a day, flooded and emerge again. This region is called the intertidal domain. Above this, we have the supratidal domain, which is brought on the water only at very high tides, and underneath is the subtidal domain, which becomes submerged only at very low tides. The strength and amplitude with which the currents and tides impact the continental shelf and the coast is strongly affected by the width of the area they are flowing through. Remember this equation? We've discussed this while talking about river flow. It says that if the width of the section decreases and the discharge remains constant or even increases, then water velocity will increase and water level will become higher. The most apparent example is observed in Newfoundland, the place with the largest tides on Earth, more than 15 meters. The movement of water masses driven by currents and tide is more complex than it would look like at first sight. Water particles move very much in oscillatory movement, essentially forming ellipses which transfer energy laterally. Such oscillatory movements form waves. In the open sea, water particles are free to oscillate and will display a fairly symmetric pattern of movements. Sea waves, like all waves, have a wavelength and an amplitude. These vary a lot depending on the driving forces. Waves associated with very strong winds can have a height of up to 20 meters with wavelengths of more than 200 meters. Water oscillations decrease with depth, and at depths roughly corresponding to half of the wavelength, no movement is recorded. We can then define the wave base, which is the depth under which water is not affected by wave movements. The depth of the wave base is roughly half of the wavelength. We've seen the morphology at sea, the processes guiding the movement of water masses. We are now ready to see what happens with the sediments which have been transported by the rivers and delivered by deltas and estuaries.